Hello everyone, this is the 8th tutorial session of the DC Microgrid and Control System, whose instructor is Professor Avik Bhattacharya sir, and I am Satyavikram Pratap Singh, and I am the TA of this course, and I am the PMRF Research Scholar at the Department of Energy Science and Engineering, IIT Bombay. So, flow of this today's tutorial session will be such that we are solving the questions related to the benefits of DC microgrid, some of the architectures related to that, and some of the components which are actually being utilized considering the constant power load in the devices due to this RE integration. So before starting the this session, there is a few questions related to that initially. So first question is related to the benefits of the DC microgrid in interacting RE sources and the storage devices. So just you have to tell me that which is the benefit for the DC microgrid in integrating this RE sources and storage system. Means what are the benefit of DC microgrid in integrating the RE sources and these storage devices. Okay, I'm giving few minutes to solve the question. Just let me know answer. Okay, let me give the solution for this. I'm giving the solution for this. This is related to the benefits of the DC microgrid in uh, integrating RE sources with the storage devices. Suppose if you go with the first option, what is saying that redundant energy or energy conversion. That is true because if you can see, suppose you are integrating, you have this AC devices and the grid is actually your AC. So when you wanted to integrate with this system, then it's easy to integrate now. But when you are integrating with this DC devices, there is a problem with these systems that you have to convert from DC to AC. But that is not the case. The suppose you are integrating the solar with the system. Solar is what is that? This is DC generating sources there. So DC generating sources there. Suppose you have the DC bus. DC bus is there. You can directly connect with this as using this DC to DC converter, and so you can use that. Suppose you are using the AC generating source. Suppose you have this wind-based system. So it's a fluctuating AC. Frequency is actually not constant. So what you will do, you convert the AC to DC, then again DC to AC, then you connect with the AC bus bar. Suppose, so here the three convergence stages are there. But when you are have the AC bus bar, then here also you need the DC to AC converter for conversion, and here you can connect with this AC. So here the problem is that suppose you are connecting with the DC bus bar, so there is a three connecting sources are there. You can connect directly. There are two convergence stage, one convergence stage is there. But when you connect with the AC bus bar, it's a two conversion stages are there, AC to DC and DC to AC. And if you connect directly to DC bus bar, this solar, it's a directly one stage conversion. So if when you are connecting with the AC bus bar, it's a two convergence stages. So the number of convergence stages. So number of convergence stages is actually lower. For the DC, it's lower as compared to the AC. Okay, so this is not a redundant energy conversion. So that is the good thing for the DC microgrid. Okay, so elimination of redundant energy conversion. No, actually it's a there uh, redundant energy conversion. No, actually it's a elimination of the redundant energy conversion. Suppose if you can see the answer as well. So redundant energy conversion is not the option because it's a elimination, because you are not going from the DC to AC conversion stage. You are directly connecting DC sources with the DC generating sources with the directly to the DC bus. Okay. So the B option is correct. A is false. If, what about the C option? It's saying increased transformer inverse current. There is a no need of going into the inverse current when it is coming to this local generation sources. So that is not the option. Fourth option is to increase the current harmonics. That is also not true. Okay. So because if you see the DC, there is a kind of no frequency component there. So there is no concept of this harmonics into that. Increase inverse current, that is for the AC. Okay. So the B option is correct. And here also the elimination of redundant energy conversion stages. Okay. So this is the second question, which is related to the which of the following practical issues with the AC network that can be overcome by the DC microgrid. So you have to tell me that there is a DC microgrid which is more advantageous as compared to AC microgrid. Okay, so that is a true because it's a more advantageous as compared to the AC microgrid. So that just you have to tell me that just you have to tell me that which are the practical actually issues with the AC microgrid which can be overcome by the DC microgrid. Okay, I'm giving you a few minutes to solve this question. Just let me know if you have any doubt. Okay. These are the some of the basic questions which you can imagine to come in the examination as well. So try to solve it. Anyone who wanted to give the answer? Am I audible? My voice is clear on what? Okay, let me give the answer for this. I will give for the next question. I will give the time for that. So suppose if we can see the practical issues with the AC grid, there is some of the issues are there related to the frequency synchronization and the reactive power flow. When you go into the AC microgrid system or AC networks, you can say, so you have this issue of the frequency synchronization that you can see from this wind-based generation system that have the fluctuating AC means frequency variable depending upon the speed. So in that what you do, you convert from the AC DC in the DFIG based system, DC to AC to DC, then DC to AC, then you connect to the grid. Okay. So here the frequency synchronization needed because you need the 50 Hz to synchronize with the grid. Okay. But if you go with the DC system, you don't need any synchronization. You can directly connect here. Okay. And also second thing, the reactive power flow. Reactive power flow actually depends upon this power factor. No? So, and the frequency, if you can see this V by X equals delta minus V. This is a line kind of reactive power flow, or in the system as well, the reactive power flow. Thus, S is equal to root P square plus Q square. But this is not present in case of the DC system, DC networks. So, that is a one problem with this AC networks. So that is being eliminated through the DC network. So first option is correct. And if you can say second option, increase the efficiency of the transformers. No, that is not the case with the DC microgrid. So it's not increasing the efficiency of the transformer. Okay. The higher current harmonic, there is no concept of harmonics. It's a not elimination, but there is a main practical issues, that is a reactive power flow and the frequency synchronization. Improve voltage regulation? No, that is not the case. So the main practical issues that happen to the AC network is the frequency synchronization and the reactive power. Okay, that is being cared by this DC microgrid system. So that is frequency synchronization, the reactive power flow. So this is third question related to that. What characteristic of the tightly regulated power electronic devices? Because all the interface, all the interfaces, if you can see the interfacing components in the RE generating sources, which is connecting to the AC main system. That is interfacing components are the power electronic based devices. Okay, so this is a devices which are in addition with this inverter as a converter can lead to the instability in a DC bus. Okay, so there is a one reason which characteristic of the power electronic devices, this PEDs have a one problem when you are integrating with this DC bus. Okay, so just you have to tell me that what characteristics actually it is. Okay, I'm giving few minutes time. Just think over it and let me know if you have any doubt. Anyone who wanted to give the answer? That is related to the one of the characteristic of this power electronic devices. Uh, if you are read it out, then you can go through these options: positive or constant load flow, the behavior, load power consumption. Then you will get some of the idea. Last 1 minute to solve this question. Okay, let me give the solution for this. Suppose you have this PEDs, which are interfacing components of with this RE sources. It have one character is that it behave as a constant power load. Okay, okay. P is equal to constant in this case. So what happens that suppose considering as power is equal to VI. So what happen if the P is equal to constant? When you are increasing the voltage, the current will dip. Okay, and when the voltage are decreasing, it means the current will go up. Okay, there are two cases. Suppose this I am this replication you can replicate it with the impedance behavior that V by I. Suppose Z is there, so voltage is going down. So in this case, current will go up. Okay, so this is the case Z will down. And the second case, if you can say Z is equal to V by I, if the voltage is getting increased, the current will go down. This is behavior that Z is increasing. Okay. So this phenomena is actually implies with this Z behavior, impedance behavior, which I will show in the future slide that how it is being it whether it is positive or negative. So the correct option is the constant power device. And if you can see the first option, what is saying the positive input impedance. No, it is not the case. Why? Because if you can see this one current is actually shown by this. So considering that the current is increasing, Z is going down, and the if the current is going down, the impedance is going up. Okay, so this is not a positive behavior because it's a negative impact which is coming from the input impedance. Okay, so it's a negative input resistance, so not the positive. So this I will explain. Low power consumption, no. Low power consumption is there, but not the characteristic of the tightly regulated PDs. High voltage tolerance, no. The correct option is the constant power load behavior. Okay. So this is a related to one of the this positive or negative impedance criteria. So that I will show in the next question. So here the one question is related to that. How do the constant power load? Suppose the your power electronic devices are behaving as a constant power loads. So which in terms of the input impedance, Z input, what behavior it can show? Okay, so there are four options I have given. Just you let me know which option is correct related to this. Just use the behavior of this Z by V by I because impedance is simply the V by I now. Whether it's a linear in the suppose you are increasing V by I kind of or I by V. So if you are increasing, the other is also increasing or the reverse case is there. Suppose you are increasing one and other is decreasing. Okay, so that kind of behavior if you can see the third quadrant or the fourth quadrant. Okay, just let me know which option is correct. Last 1 minute. Okay, let me give the solution for this question. What I've told that if you see the characteristic that it's a power is equal to constant, so there are two cases that. So if you consider that power is equal to Vi, so if you increase the voltage, the current will drop down, or if you decrease the voltage, the current will go up. Okay. So this behavior is explained in such a way that this is Z equal to V by A. If you're increasing the voltage, the current will dip, considering the Z as a uh, it will increase. So if you see that this Z behavior that V by I is increasing, Z will drop down. Same with this V. If we are decreasing the V, the Z will drop down. So from this, let me remove this and draw it again. So if you're considering this axis as V by I ratio, so suppose you are in this quadrant, okay, in the first quadrant. It will depict that if you're increasing the current, the voltage will increase. Okay, current will increase, this means that the voltage increase. So that is the not the case in this case. What is happening that if you're decreasing the voltage, current will. Suppose you are in the second quadrant. What will happen here that if you are increasing the voltage, okay, the current is dropping down. Current is dropping down. Okay. So this can be the one scenario. Okay. So if you see the fourth quadrant, this uh, third quadrant, okay. So in third quadrant, if you can see that if you are increasing the voltage, and the current will also increase, but in it is a negative, but overall it will become the positive only. So this is the not the case. In the fourth quadrant, if you can see the if you are increasing the voltage, if you are increasing the current, the voltage is dropping down. So second and the fourth quadrant is actually the answer. But what happens in the both the cases, in both the quadrant, it's a negative impedance. No, negative impedance. So because the V by I ratio in the both cases is negative. In one sense, the current is negative. In one sense, the voltage is negative. Okay. So here the so what it will impact that they exhibit the negative input resistance. Okay. So if we are considering the power load is a constant for this power electronic devices, so it will actually replicate with this negative input impedance. You can see from the second and the fourth quadrant itself. So it's a behavior is actually replicating with this negative impedance. So they execute, that is the solution. So coming to the next question, which is related to that, what is the need to be ensured in the all the operating conditions to achieve this safe and reliable microgrid performance? Okay. So for this microgrid operation, the reliability is also very important. So for ensuring this reliability, your component should operate, means achieve a safety issue, and the reliability is one of them. If you can let me remove this. So the operating condition should be the safety and reliability. So just you have to tell me that which of the need to be ensured in this operating condition, in this safety reliability, in this operating conditions, What things must be ensured? Low impedance, constant voltage, high power operation, dynamic stability. In case of the microgrid performance, think wisely, and you will get the answer for this, for sure. Last 1 minute to solve this question. Okay, let me give the solution for this. Actually, if you can see this microgrid performance, uh, didn't got any answer for any of the question. So this is operating conditions to achieve the safe and reliable microgrid operation. The high power generation is not the case because the operating reliability is the issue with this PV generating sources and the wind-based system. So the reliability is major the criteria, but it is not ensured in that. So this is not the case. The dynamic stability must be ensured because if you are generating the PV and it is not stable at the grid connection point or the output side, so that is not the good thing for the operation of this microgrid. Okay, so the dynamic stability is actually very important. So constant voltage, low impedance, though not the case. Okay, dynamic stability must be ensured. So the answer is this. Okay. So here the one question related to the typical cause of the instability in the DC microgrid. So just you have to tell me that which are the options so can be the possibility for the instability is the DC microgrid. Okay, go with this criteria that suppose you are having the one generating source. Suppose one of the generating source is there. What do you connect that? You connect this EMI filter. So here at this point you get the one impedance related Z input and then you connect DC link or you are connecting with the inverter and this is Z out kind of. Okay, so you have to maintain that it should be balanced condition. Z input should be higher than the Z output. With this, I will explain that what is the cases. Just you have to tell me that which are the actually the problems related to that. A cause of the instability in the DC microgrid. Okay, I'm giving you a few minutes to solve this question. Just let me know if you have any doubt. Has anyone got the answer for this question? Okay, let me explain this. Let me explain this question. What is saying that what is the typical cause of the instability in the DC microgrid? The excessive power load? No, that is you can connect it. The excessive power is not an instability issue, but the instability issues is impedance mismatch between the filter and the power converter. This I will explain. We have the slides for that. I will explain that how this impedance mismatch between the filters and the power converters will come. Voltage fluctuation will be there, but it is not a constant because it is handled by the through the DC-DC converters. Okay, so the voltage fluctuation is not a issue. Inadequate power supply, no, because if you're connecting the battery storage system, so this is not the issue in adequate power supply. You can have the battery bank when the generation is not enough. Okay, so suppose the battery storage is not there, then it is a kind of power stability issue is there, but power supply issue is there, but it is not the instability, because if the generation is not that much, because the demand is higher than the generation, and you are thinking something that how this demand should be met, so in that case the difference is higher. Okay, so what the simply the inverter will do, it will shut down that it will not supplying any of the power. Okay, okay, so this is a kind of one of the cases, but it is not a stability issue, but the impedance mismatch is the, because it is inside the converters. Okay, in between the converters or in between the power convergence stages is there. Okay, so this is okay. Okay, so this is the one of the question related. This I have already explained, but I'm thinking that you should go through this formation how this should work. That what kind of load actually loads introduces negative impedance characteristic in a low frequency ranges that tends to oscillate with the power supply. Because I've explained of the 50 here that what kind of power sources should be there. Just let me know if you got that point. Does anyone got the answer? Let me check. Okay, I've got the one answer as well from the 11. It's a constant power load devices. So let me explain this. Did I already explained that CPLs are there, constant low power load devices are, which having the negative impedance, which I have already explained how this second and fourth quadrant is there, which is actually responsible for this negative impedance under the low frequency ranges, because it's not a high frequency system, because we are operating at a 50 Hz. So not a high frequency terms, it's actually with this 50 Hz system that tend to oscillate with the power supply filters or output impedance. Okay, so that is true that constant power load devices are there. So let me explain, ask one more question, that which of the following introduces a destabilizing effect in a practical application? Okay. So just think of that, whether it's a heating of the resistors or whether it's a transformer, destabilizing effect. Okay. So stable means whenever if any disturbance can be there, your system should come into the come into a stage when which was there initially. Suppose you have this frequency stability. Suppose you are operating at 50 here. So what if the fault or something comes? So it is like that you should oscillate and come to the 50 here. Okay, this is the oscillating time basically. So this is system is stable, but how much is stable you can define with this time duration. Suppose one system is there operating at 50 here and it go on oscillating. So this is a kind of unstable system. Okay, so that is a kind of stability and instability kind of there. But suppose the disturbance come, it will come back to the previous state what it was there in before. Okay, so just let me know which of the option is correct related to that. Okay. Okay, I got the one answer as A. Okay. Uh, I'm giving you 1 minute to more to solve this question. Um, if anybody else wanted to solve, just wait for 1 minute and then I will explain this question. Okay, let me explain this. The correct answer is A actually. That is true, which I was given the answer by Lavanya. So the passive filter resistive heater step up transformer, that is not a stabilizing. This is kind of stabilizing system is there. The passive filters are there which actually used to filter out the high frequency harmonics, and the resistive heaters are there. They are not destabilizing. They are actually, this is the resistive heater is a load. Okay, step up transformer that actually stabilizes the voltage. Okay, so this is a destabilizing features, that speed regulator motor drives, okay, and the electronic loads, okay, which actually introduces harmonics, and speed regulator motor drives actually introduce some of the fluctuation in the voltage, suppose in the insulation itself. So this is a kind of destabilizing issue. So coming to this next part, next question, this is related to that which type of converter which is being used to demonstrative CPL example for explaining the stability in the phenomena in the DC microgrid. What I explained, their concept of CPL, constant power load devices. So what happens that this power electronics devices are there having negative impedance, negative Z. Okay, so that is a kind of disadvantageous feature. So one of the stability criteria that you wanted to stabilize the system, so you must use one of the converter. So which converter do you think can be used for that purpose? Okay, just let me know if you are able to think of that. Last 1 minute. Last 1 minute to solve this question. Okay, let me give the solution for this. Actually, what happens that if you are using the demonstrative this CPL example for the explaining this stability phenomena, you just need a buck converter for that. Not a five-wheel forward converter, not a boost converter, because you don't want to boost it up now. Uh, you have the certain voltage at a one end, you wanted to make it at a stable condition. No? So voltage you wanted to maintain as a constant. Okay, so but buck converter what it will do? Buck converter, if you can see the topology, what is happening that you have this switch initially, then you have a diode, and you have this output filter. This so what it will maintain that I is equal to constant at the output side based upon the what are the this inductance you are using. Okay, so I is equal to constant is actually happening the output side. Okay, so that you actually need. Okay, so that the current should be constant and the voltage could be variable depending upon that. Suppose the power is there, it will reduce based upon the voltage. Okay, if your voltage is higher, then power should be higher. And same versa. Suppose the voltage drop down, the reactive power injection should be higher. The voltage higher, the reactive power injection should be lower. If the reactive power injection should be lower, then P will be either means most probably will be higher. So it's a constant of S is actually maintaining as a constant. Okay, so that's why the buck converter is being used. So output side you have the one inductance there which stabilizes the current at the output end. Okay, so that is actually the explanation for the why you use the buck converter for that purpose. So we have the one more question related to that, which is a common approach for modeling and analyzing the switching power converters in the microgrid. Okay, so because if you are studying this microgrid and you are actually wanted to design some of the control schemes, okay, so there is a systems that you come to that you have this differential equations models. Suppose you are explaining that I is equal to C dV by dt, one of the equation. It's a kind of non-linear. Okay. So what you wanted to do, you wanted to linearize this system or whatever you wanted to do. Just let me know the answer because I have already given this. Averaging and linearization can be the options. Okay. So time domain simulation is not the correct option because you go with the S domain analysis for the stability purpose using the Nyquist criteria and all. So averaging and linearization one of the suppose you are using I is equal to CdV by dt. You just wanted to linearize it that I is equal to T2 minus T1 is equal to CV2 minus V1. You just wanted to linearize based upon the situations. Okay. So the averaging and linearization is the one of the common approach for modeling and analyzing the switching power devices. Okay. This is one of the questions related to the modeling of the DC microgrid. There are two subsystems in the full scale system microgrid. It can be broken down. Suppose you have the full system model. It can be broken down into the two subsystems. First subsystem and the second subsystem. Okay. Just let me know which of the options are correct. Okay. Related to this. Okay. Which could be the first subsystem, which could be the second subsystem. Okay. Just think over it. Any answer from anyone? Last 1 minute to solve this question. Okay, let me give the solution for this. Okay, so the two system which you create for the full system model, that is actually the one from the source side, source subsystem, and other is the load subsystem. That is the only subsystems you actually replicate now. So load system is that you have the R, L, C, or the combination of the all the things. So you can represent with that one subsystem. Source subsystem is that you have to model that. Suppose the PV based model is there, then you have to model that, and you have the wind based models, and you have to model that. Then you have the battery storage system. You have to model the battery storage system. So the modeling can be two. It can be divided into two subsystems: that load subsystem and the source subsystem. Okay. So this is answer. So let me go through the some of the dynamics of the DC power supply. Okay. So here the one thing is that the common DC bus realized by the means of the power supply unit with a line filter to which a point of load buck converter is applying a resistor to. Here, if you can see the why we are using the buck converter that I have explained with the one of the question, and why use the line filter in between. So if you can see the topology, switching voltage regulator system, which is there. From the source side, if you can see, this is a VS, and this is the input filter, and output of the input filter that is expressed at the ZS, that is the source impedance. And then this is the VDC plus minus that common DC bus IPOL. This is the current which is flowing to the point of load. Okay. And this is the point of load converter, just GVDS, that is the POL converter at this point, that is the Z input. And this is the load, that is suppose you are using the resistive load, so you are taking the load as a one of the input. So what you wanted to do, you wanted to stabilize the voltage, okay, maintaining the voltage as a constant, okay. So what you will do, you take the reference from the V load as a one of the parameters, then multiplied with the sum of the gain, and then subtract with the V reference what you want. Then submit it to the voltage gain, that GVS, and divide by the voltage. So if you are dividing with the voltage, then you will get the impedance value. Then you feed into this GVDS. By doing that, you will get the Z input as a one of the parameter into that. So you can control based upon that. Okay. So the input filter which is used for the two functions, that is reflecting the current drawn from the supply in, that it take, if you are using the buck converter in between, same as a, so you it the I can be made as a constant. So that is one of the parameter that using the buck converter in after the line filter, that POL. Okay. Then attenuating the high frequency variant at the input. So that is also one of the filter, the input filter, LC filter is there. So you wanted to reduce the high frequency component which is coming from that. Okay. So it have the two actually the functions. One is the flattening the current drawn from the supply in. Second is the attenuating the high frequency variation in the input terminal of the POL converter. Okay. So, but while the improving of these two functionality, there is a supply side brings the additional dynamics. The dynamics in what sense? Undesirable interaction with this POL converter, which is system is not properly designed. Okay. So this interaction can be seen through the ZS and the Z input. So if the voltage control loop, which is this voltage control loop, this is the voltage control. If it is not working perfectly, then it means that the power on the resistor will not be constant value. Okay. So if the power is not constant, it means the power is not maintained as a constant value. So it means that it will have the certain power fluctuation, power instability, if you can say, instability in between both the system, in between system. One system is there, if you can see from this end. Second system is that this. Okay. So in case the VDC decreases, suppose the voltage as the VDC decreases, it means the current automatically increases. So what that I have actually explained that it have the negative impedance criteria, negative, because if the voltage is decreasing, the current will increase. Okay, to drop down this effect. Okay, so automatically increase in order to maintain the constant power, causing the incremental resistance, that resistance will increase. As seen that the DC bus side, because it's a negative, so if it is a decreasing, negative means it's increasing. Okay, appearing with a negative incremental change. Okay, that I will explain here. That suppose the R input is there, R input is the del VDC by del IPOL, IPOL which is coming from the source side, and del VDC which we wanted to maintain. Okay, through the external loop you are connecting. So if you differentiate that, VDC is will be power divided by delta IPOL. Okay, so this is the, it will come with this. If you differentiate with that, that VDC is equal to power divided by del IPOL. So in this case, if you can see that it will come with the negative, that this R input is equal to minus P divided by IPOL square. Okay, so here if you plot with this VDC versus IPOL, you will get the negative incremental impedance is introduced by the POL converters. Okay, so that is the same phenomena, that negative it will come, that R input is negative. Same, if the power you wanted to reduce, the R input will increase in this sense, and the IPOL if you wanted to decrease or increase, that will similarly affect the R input, which is negative. Okay, so this is the one phenomena, that if the power maintaining as a constant value, so that is the one of the issue, that it create an instability in the current. Okay, so you wanted to maintain the IPOL as a steady state value. So any analytical expression, that you need a closed loop input impedance, that similarly which I have shown in the previous slides as well, and also the control loop input impedance. So blows both system, that it is a output side or the input side, the input side both you wanted to maintain as a constant level. Okay, so that is same system, and also that there are some gains are involved. So that if you can see here, that HS, GVS, okay, GVDS, so all the gains have certain terminology associated with definitions associated with that, and there is some phenomena that when you wanted to control one thing, that the other thing will be controlled, which I have explained here elsewhere, written here, that is same with the slides. Okay, just you have to remember that here that you are using the EMI filter in between, then you are connected to the constant power load devices, that is invert IB, that is actually the power electronic devices. Okay, so if you are taking the LC filter in between, that similarly, that the high frequency component you wanted to minimize one thing, and you wanted to maintain current as a constant. Okay, uh, so that is actually the important one. If that is similarly can be explained, that if you can see this single stage LC filter, and how the stability actually being considered in this situation, that is through the uh, Nyquist criteria. Nyquist criteria, it is this stability can be explained, so that you can also figure out that -1 0 encirclements, and n is equal to P minus Z, number of open loop poles, that is one of the way. Okay, just you have to remember that the how the stability of the these systems can be followed through the Nyquist criteria. So instability between the source and the filter may occur if the filter impedance becomes lower than the source impedance. So what you wanted to maintain that the Z input is always should be greater than the ZS. Okay, this is the one thing we wanted to figure out. So that instability can be figured out through the Nyquist criteria, that what you wanted to maintain. Okay, so based upon that, I have one question related to that. The what are the basic building blocks of the renewable base energy based DC microgrid? Okay, just this is a kind of easy question. Just let me know if you have any idea of that. Last 1 minute to solve this question. Okay, let me give the solution for this. That what are the major building blocks of the renewable? That is a power electronic converter. Okay, a basic question. That is basically understood by yourself itself. So here are the one question related to the PID control scheme. Okay, control technique. That is the PID control technique. So it has certain disadvantage. Okay, related to this DC microgrid. So just you have to let me know which of the options are correct related to that. I'm giving few minutes to solve this question. Just think over it. Okay. Okay, let me give the solution for this. Why the PID control scheme techniques are insufficient? Because they have the certain problem. Certain problem related to what? Related to it's a B option is correct that they cannot regulate the DC bus voltage and stabilize the system with the CPL and uncertainties. What happens that when you are having this constant power loads devices, in these situations, your voltage, your current is actually not constant. So what happens that the if you are decreasing the voltage, current will increase, and similarly with that, when you are increasing the voltage, current will decrease. Okay, so this current is not actually constant. So if certain phenomena occurs that your voltage got dipped at the output side, so what will happen? The current is going to change. So if your current going to change, it means that it is actually creating a problem in the maintaining a stability in the both the systems, because the one side current is fluctuating. Based upon that, the current is taken from the source extra current. Okay, so that is not a constant value. So it is the duty of this control scheme that it should stabilize the current in that situation. So this PID based controller is not able to regulate the DC bus voltage and stabilizes the system. Okay, so if the voltage could be stabilized, that V is equal to constant, so in this situation also that the current will be not fluctuating, non-fluctuating in that sense. So suppose you are have a 12 volt system and you are increased to a 16 volt or 18 volt. In this situation, the current will going to change. So if your voltage, your design output is need a 16 volt, when you can use that boost converter in between that, so it will automatically boost to the 16 volt. So current is not going to change, or otherwise it will going to reduce. Okay, so that is a actually disadvantage of that. Okay, so one more question related to the instability problem. What are the root causes? Root causes related to the instability problem in the source load interconnected DC systems. Okay, that you can guess also from the lectures or from the questions which I have previously shown. Okay. Okay, I got the answer as a B. That is actually true because the impedance interaction was the one of the phenomena that is causing the instability in the problem. That is true that impedance interaction is there. Okay, voltage not drop is not the issue because the source load interaction in between when the input side which is interacting with this EMI filter, then you have this ZS, then you have this Z input. Just you have to maintain this ZS and Z input as a constant. Okay, not constant. Z inputs always should be greater than ZS. Okay, so this phenomena is there. That is impedance interaction is the one of the issues. Okay, coming to the one of the major important points that damping. Damping is the DC microgrid. So this is the related to that only. There are two types of damping. That is active damping and passive damping. Just let me know which of the option is correct related to this methodology. That which method uses the resistor, capacitor, inductor to improve the system stability in the DC microgrid. Okay. Just let me know which option is correct. This is related to the damping only. Okay. Yeah. It's of two types. That damping is active and the passive. Just which methodology is actually using the resistor, capacitor, inductor to improve the stability? Okay, let me give the solution for this. Okay, so this methodology which is using this R, C and L values for the improving the stability is actually the passive stabilization. Okay, so this is a kind of passive filtering is there. So active components is actually don't use this resistor. Resistor actually dissipating elements. So and capacitor inductor are the storing. So the answer is a passive stabilization. Coming to the next question. Next question related to this which component actually in the passive damping which is typically inserted between the switching modes power converter and the source of the comply with the EMI standard. Actually it is already known from the question itself, but let me guess that which of the options are correct. Okay, let me explain this. You see, also the EMI in standard, you can guess it, there is EMI filter is only. So in the passive damping, the EMI filter is actually inserted between the switching mode power converters and the source. Okay, that is the input side, that is ZS. Uh, Remove this. This is the ZS, and this is the EMI filter which is being inserted. Okay, to comply this as switching mode power supply, it's there. Okay. So coming to the next question, this is related to some Nike's criteria that what are the instability in the source filter system which occur when the filter input impedance become greater than less than at a output resonance frequency. Okay. So when the resonance frequency is there, what could be the impact that filter input impedance is there and the jet source output impedance is there. So what are the relation between them? Okay. Just you have to tell me that. Okay, let me explain this. Actually, jet input should be what is saying the jet input should be lower than the jet output. Okay, that is the one criteria. And damping of the LC filter, which is passive damping, so that actually being known. So for reducing this should reduce the output peak at the cutoff frequency. That few of the things you, if you go with this, what is written inside of this documents of the NPTEL sessions. If you read it out, you will get the answers of that. Okay. So here the one question related to the small signal impedance to constant power, that is same that negative impedance, one of the answer. Okay. So here the one of the question related to that, what is the common cause of small signal stability? Okay. Here also that interaction between the badly scaled positive and negative impedances. So just there is a less time. So just I am going to read it out the questions. Okay. Just what is the common cause of a small signal stability in the DC microgrid? That is actually the interaction between the scaled positive and the negative impedances. Okay, how? So instability is actually occurs due to the interaction between the component between the positive and negative impedance. If these impedances are not well scaled, they are create feedback loops that leads to the instability in the DC microgrid. Okay. This second question is related to the which stability analysis method is commonly used for power electronic distribution system, that is impedance admittance methods. Okay. So here the explanation is such that power electronic distribution systems that is often use impedance method for stability analysis. This method helps to analyze how the source and load impedance affect the system overall stability. Next question is that according to the middle book criteria, which is a system considered stable. Okay, let me explain that what is the middle book criteria is there. So the middle book criteria is a stability criteria that can be used to determine if a DC-DC converter is stable. Okay, so stability condition, if you can see, such that the magnitude of the load subsystem, that ZL, must be greater than the source. Okay, jet I have also estimated jet input should be always means lower than this ZS. Okay, So this is two criteria you can filter it out, that ZL is always should be greater than the ZS. Impedance ratio criteria is that ratio of these impedances is known as the system minor loop gain. Okay. Nyquist criteria is that Middlebrook criteria is based on the Nyquist criteria only, which states that the system is stable if the curve doesn't surround the point -1, 0 on the complex plane. Okay. And the stability reason is that Middlebrook criteria, it stabilizes a circular region of the radius T naught, which defines the smallest stability region. Okay. And this criteria can access the stability margin that result to adding a load. Okay. Main filter out points are that it is actually a stability criteria for determining whether a DC-DC converter system is stable or not. Okay. So the magnitude ZL should be always greater than ZS, and -1, 0 criteria that if it is a curve is actually surrounding the -1, 0 on the complex plane or not. Okay. So related to this is the stability only. Okay. So moving forward, that so which criteria allows the Nyquist diagram to occupy a larger region of the S-plane and the less conservative than the middle group criteria. Okay. So this is actually the Nyquist stability criteria only. Sorry, opposing. So this is opposing augmented criteria is there. Okay, opposing augmented criteria is there. So the explanation says that the opposing augmented criteria is less conservative than the Middlebrook criteria because it allows the Nyquist diagram to occupy a larger region than the S-plane. Okay. So the Nyquist plot is such that it will occupy the real part and the imaginary part. They have the certain reason to in which you can check the stability. But the middle, in case of the Middlebrook, but if you go with the opposing augmented criteria, is actually less conjective because it's has a larger plane to explain it. Because you can don't have this -1, 0 condition to suppose your plot is such that. So you get the reason overall the system is the plane, okay, to explain the stability. So here the one of the question related to the common limitation in the classical linear control methods when they use the DC-DC converter with the constant power loads. This is actually the related to this. This ensures that a small signal stability, but not in this. This they are ineffective for the linear system. So the main point is that it is actually they ensure the small signal stability but not the large signal stability that we have seen as well. So classical linear control method are effective for the small signal stability but struggle with the large perturbation when the step load changes can occur. Okay. Coming to this next question, that the main purpose of the feedback linearization in the DC microgrid to cancel out the non-linearities. Okay, so you have the systems which having the non-linearity and linearity. Just you have introduced by the CPLs. Okay, constant power load because the current is actually variable in that case. So you need a constant voltage maintaining phenomena. Output side also, input side also by consuming taking the feedback from the load side, that plus minus V output. Okay, so just you have to compare that how the linearization can be done and the taking the feedback from the system and making the system linear, and the linearity should be cancelled out. Okay, and also the one question related to that is in feedback linearization, what is the role of a nonlinear feedback that actually cancel out this or the same questions here. Okay. So going to this sliding mode control, I'm giving this question to solve you because it's a simple question that sliding mode control primarily using the DC converter. What is it? Just think of it. Okay. I'm giving you a few minutes to solve this question. Okay, I got the answer as a B. So the sliding mode control actually primarily used for ensuring this robust control in the presence of this. So this is the end of the today's session, and also I'm explaining that the sliding mode control is a robust non-linear control technique which is used with uncertainty, making it suitable for this. So today is the last session for this regular tutorial regular tutorial sessions. So one tutorial session is I think on Sunday. So that is related to the understanding the revision session is basically where we are going to revise all the things which we have done in the course, and also the some of the questions related to that is initially related before the exam, I think. So most probably that I will be explaining few of the questions only, and which is relevant and based on the assignments only. So I'm not going into depth of the course, just upper layer, so that you can be comfortable with the easy questions first. Okay. And also you have to remember the few of the things related to that, which is related to exams as well, that you should try to solve the assignments very carefully. Okay. Here I am given the depth question, but you should go with the easy questions as well related such that DC to DC converter basics, AC to DC converter basics, DC to AC converter basics, kind of. Okay. So the basics you can, if you have the knowledge, then you can solve any of the questions. Okay. So here the few of the things which I wanted to tell, and also just go through the assignments, and which is more important because there the easy questions is also there, that like Thevenin impedance based question, Norton based easy question, and KVL KCL based question, so that you can solve and be familiar with that concept as well, so that it could be easy to understand. Okay. So this is the overall tutorial session for 8 tutorial session, in which we have studied few of the things related to this benefits of the DC microgrid. Second, we have studied the what are the practical issues into that. Then we have studied this what kind of characteristic that regulated PEDs actually follow. Then we have studied this constant power load behavior in terms of the Z input impedance. Then we have also studied that what kind of stability is needed for the safety and the reliability of the microgrid. Then we have studied the typical cause of instability, and also the who causes this negative impedance at a low frequency, that 50 Hz and all. And also we have studied what are the destabilizing effect in the practical application of the microgrids. Then we have studied this what are the CPL example, the demonstrative CPL example, that in which the converters, which kind of converters is used for the stability phenomena. Okay. And then the most common approach for modeling and analyzing the switching power converters in the DC microgrid, one of the question, that is averaging and linearization. Then we have studied the two subsystem in the full system model, which can be broken down and studied, because in the modeling you have to bifurcate the system, then you have to analyze and by connecting the all. Okay. So here the two things are there: load subsystem and the soap subsystem. And then we have studied the dynamics of the DC power system, and then how the components are being there, and what are the gains are there, how the closed loop system is there, how the V load is compared with the V reference, that we have studied. Then we have also shown this what are the incremental resistance mathematically can be shown, and how the negative components come into the picture. There are some gains related to that which can be tuned to make the system that Z input greater than ZS, and the major stability criteria for the study is the Nyquist criteria. That is whether it is curve is actually following or enclosing the -1 0 or non-enclosing. Based upon that, n is equal to p minus z criteria is there, that you have to see. And also we have studied what are the building blocks of this power, whole of the RE systems, and then the what are the uh, disadvantage of the PID based system. Then we have studied what are the root cause of instability problem in the source load interconnected DC system. And also we have studied two types of damping phenomena, that active and passive. One example we have seen from the passive stabilization. Then what are the components inside of this system, that is the EMI filter where it is being placed, And then we have studied that what are the relation between the Z input and the Z output based upon at the resonance frequency itself. Then we have studied the primary purpose of the damping resistor in the AC filter with the passive damping. Okay. Then small signal stability, how this power system is related to that. And second, what type of small signal impedance criteria based upon the constant power devices. Then we have also studied this common cause of the small signal stability in the DC microgrid. And then one of the stability analysis method related to the power electronic based distribution system, that is impedance admittance bits. That is same criteria that Z inputs would be greater than ZS. And also we have, according to the Middlebrook criteria, we have studied which system to be considered as stable. That is the when the Nyquist contour, that is ZSYL, remains within the unit circle, that you can say that it's a stable. And the key disadvantage of the Middlebrook criteria is that it leads to the artificially conservative designs, okay, which is not actually imposes strict stability requirements. So this is a problem with this Middlebrook criteria, and how this can be addressed, this disadvantage, through the opposing augmented criteria. Okay, so this is the, it have the larger a larger reason for the stability as compared to the Nyquist diagram, this Middlebrook criteria. So the opposing augmented criteria is better as compared to the Middlebrook criteria. Okay. And what are the common limitations of the classical linear control method in the DC-DC converters? Then we have also studied that what are the main purpose of feedback linearization, because we have to linearize the system first for this study. Then feedback linearization, what is the causes or rule of the nonlinear feedback